In this video, we're going to cover proof by mathematical induction. So, mathematical induction is a method of proving a statement true for positive integers n. Also called inductive proof, this proof relies on proving a statement true for a specific value of n, then generalizing to all cases. There are many different ways of proving mathematical statements, and you may have already used proof by deduction that use known facts to prove statements. We use proof by mathematical induction for statements that involve integer values of n, for example sequences and series. It relies on proving a specific example and then moving to a general conclusion. If we need to prove that a statement is true for all positive integers n, there are certain steps we need to take. Step 1 is to show that the statement is true when n is 1. Step 2. Assume the statement is true for some positive integer value n equals k. Using the assumption, prove that the statement is also true for the next integer n equals k plus 1. And then come up with a conclusion and state why the statement is true for all positive integers n is greater than or equal to 1. Now this method only works if you follow all the steps. If you can prove a statement true for several values of n, but then not for n equals k plus 1, it is possible that it is true for some values, but not all values. So now we're going to answer a question, and we need to state whether each statement can be proved by induction. Now on your screen we have n bracket n plus 1, n plus 2 is divisible by 3, where n is a positive integer. Now, we can prove this. This is possible, yes. Now, the reason this is possible is because n is a positive whole value. A equals n squared is the area of a square where n is its sides. Now, this is not possible. This is no, and the reason this is no is because n is a continuous variable. It is not a whole number. Alright, next we have proof by mathematical induction if n is an integer. On your screen we have it at 3 plus 10 plus 17 plus ... until we get to 7n minus 4 and n over 2 bracket 7n minus 1. So the first thing we need to do is prove that the statement's true for n equals 1. At this point we're going to be focusing on this section. And what we do here is we say we have the left hand side equals the right hand side. So our left hand side is going to equal 7 times 1 minus 4, which is 3. Our right hand side is going to equal 1 over 2, 7 times 1 minus 1, which also equals 3. So the left hand side equals the right hand side, so we can assume that it is true for n equals 1. The next thing we need to do is assume the statement's true for some positive integer value n equals k. So what we do there is we start to rewrite our series or sequences. 3 plus 10 plus 17 plus ... plus, now instead of n we have k minus 4 equals k over 2, 7k minus 1. And that is all there is for step 2. Next we move on to step 3. Using the assumption, prove that the statement is also true for n equals k plus 1. Now what we do is we substitute in our n equals k plus 1. So we still have 3 plus 10 plus 17 plus ... plus 7k minus 4 plus our now k plus 1 over, oh sorry, not k plus 1, I'm getting ahead of myself, plus our square bracket 7k plus 1 minus 4 equals k plus 1 over 2 square bracket, just to make things clear, 7k plus 1 minus 1. Now I'm going to tidy that up a little bit by doing some simplifying. So we know 3 plus 10, this is all going to stay the same. Except if we expand this out here, we're going to end up with 7k plus 3 equals the k plus 1 over 2. Do the same thing over here, we can expand this out, and we end up with 7k plus 6. So now we do the same thing that we did with our step 1, where we had to prove that n works for left hand side and right hand side. So this time we're going to focus on the left hand side. And we know that this section here, based on our assumption, equals this up here. So what we can do is we can substitute that in. We know that that's going to change. So that goes to k over 2, 7k minus 1, plus 7k plus 3. Now I'm going to bring out the half as a common factor, which means that we're left with k here, 7k minus 1. We don't have the 7k plus 3 anymore, because if I was trying to bring out the half, what do I need to multiply that half by to get back to the 7k? So 14k plus 6 goes there, because a half times 14k is the 7k, a half times the 6 is the 3. Alright, now that I've got that, I can simplify what's in the square bracket, so I'm left with 1 over 2, gives me 7k squared minus k plus 14k plus 6. Simplify that down. 7k squared plus 13k plus 6. Now that is a quadratic, which we can solve to get a half, k plus 1, 7k plus 6, or k plus 1 over 2, 7k plus 6, which is our right hand side. So we have proved that the left side, in terms of when n equals k plus 1, does in fact equal the right hand side. So now that we've done that, we can state why the statement is true for all positive integers. So we can write, hence, this statement is true for n equals k plus 1. It is true for n equals 1. N equals then 1 plus 1, which is 2. N equals 2 plus 1, which is 3, and so on. So the statement is true for all n is greater than or equal to 1. So to end the video, we're just going to do a quick recap because there was a lot going on there. Ultimately, it comes down to these steps, and we need to prove them all. So step 1 was to show that the statement's true for n equals 1. Step 2 is to make the assumption that the statement is true for n equals k. Step 3 is then to use that assumption and prove that the statement is also true for the next integer, n equals k plus 1. Once you've done this, you can then write a conclusion, which is to state why the statement is true for all positive integers n is greater than or equal to 1. Now remember, the method only works if you follow all the steps as I did in the example. Doesn't mean just because you can prove for several values of n, if you can't prove it for n equals k plus 1, it might not be possible that all values work.